Hi, my name is Shade Summerall. I am pursuing a career in medicine as a physician specializing in infectious disease. My teammate for this project is Kendall Phillips. She wishes to get her doctorate in occupational therapy. Today I'm going to talk to you about a new form of technology called Crispr. Crispr stands for Clustered Regularly Interspaced Palindromic Repeats. CRISPR is a new technology that cuts certain DNA strands to give a person the desired genome sequences that can avoid disease or show certain traits in crops, bacteria, and maybe one day humans. The old saying that you can choose your friends, but you can't choose your family, may no longer be true with the implementation of CRISPR. CRISPR is pretty complicated, but we can look at the slide shown here to get a general overview of how it works. First, the Cas9 protein, which acts as the scissors in this mechanism, forms a complex with guide RNA in a cell. The complex then attaches to a matching genomic DNA sequence, adjacent to a spacer. We can see on this slide that the spacer is shown in yellow. It works as a guide for the genomic sequence to attach to the main strand. Then, the Cas9 RNA complex cuts the double strands of the DNA. Finally, programmed DNA can be inserted at the cut, which changes the overall makeup of the strand. One of the many functions of CRISPR is used for editing the DNA of certain plants to make them how the person manipulating the DNA wants it. That way, we can edit a plant's DNA to make them taste better, make them more nutritious, or have them able to mature more quickly to allow more plants to grow in a shorter period of time. This could help solve issues with world hunger or even just reduce the rising cost of groceries. The obesity problem in the United States partially stems from the fact that people think healthy fruits and vegetables are too expensive. But when we can control what grows and how fast it grows, the supply will greatly increase, making prices go down. Even the issue of running out of food due to overpopulation could be fixed by simply manipulating the DNA of plants to increase crop yields and the nutritional value of food. Another advantage of CRISPR is the scenario discussed here. In this example, Susan has sickle cell anemia, which is caused by a single-letter DNA mutation. Scientists make a guide strand of RNA that matches the mutated DNA sequence. Then the molecular scissors are added into this sequence, also known as CRISPR. This is then injected into Susan, where the guide RNA identifies the mutated DNA and cuts out the single mutation. The healthy strand without this mutation then replaces it. After this process, Susan should no longer have sickle cell anemia or any of the harsh side effects of this disease. The diverse gene pool of hereditary disorders has made them difficult to cure in the past. CRISPR can be personalized to any gene for which this scenario includes Huntington's, Alzheimer's, and Parkinson's disease. For this example, when studying rats, scientists were able to target the faulty rat genes with CRISPR and eliminate mutations. These outcomes can be used to create new drugs to potentially cure these horrible diseases, rather than having everyone go through the expensive process of editing and cutting out DNA mutations. This advancement could be used to cure diseases like Huntington's, Alzheimer's, and Parkinson's, and eventually by creating a drug or vaccine so these terrible diseases will no longer exist. Even though CRISPR is looking into the future with high expectations of treating horrible illnesses and creating more sources of food, there are still many kinks that need to be worked out. When inserting CRISPR into an embryo that is expected to have a certain illness, it is difficult to aim this gene editing sequence at a specific target area where the mutation has been detected. In research, it has been very difficult to put this injection directly into the brain of mice due to the limitations on what the blood-brain barrier will accept. These challenges make it difficult to test on humans because many of these issues may take years to work out before it is ethical for human testing to even begin. From curing terrible, debilitating diseases and helping feed the hungry, the advantages of CRISPR are apparent. However, there are some great ethical concerns once we start altering the DNA of human beings. As this photo shows, with the ability to change one's defining characteristics, we could choose what eye color and hair color our children have, how athletic and smart they are, and even how physically attractive they are. Where could we draw the line from curing terrible illnesses to custom designing our children? This could scrape any last individuality a person could have, and alter every feature about a person to make them just right in our eyes. Thanks for watching. Please consider the discussion questions to follow as some food for thought. If CRISPR could be implemented in humans, do you believe there would be an even greater gap between what the wealthy can afford with this DNA editing versus what the poor would have to deal with regarding diseases and personal characteristics of their children? Would this result in an even greater class divide in healthcare for our nation? And should genome sequencing be used to change the DNA of children to create people who have more positive qualities than negative ones? Or should DNA be up to chance? Is modifying DNA to build babies ethical? Be sure to check out our references. They're a great place to learn more about this innovation.